Hey, Chattanooga. Today we're going to go over topics that are covered in Chapter 3.5. And what we're going to focus on is how we can predict the charge of an ion based upon the position in the periodic table in which the element that forms that ion is located. And so just as a reminder or review, an ion is a charged particle that's formed from an atom. And we have two types of charged particles. We have atoms that can lose electrons to form positively charged particles that we call cations. Or we also have atoms that gain electrons to form negatively charged particles called anions. Big question is, well, why do atoms lose or gain electrons? We'll learn more about this when we get into our chapter involving electrochemistry and redox processes. But simply stated, atoms typically want to lose or gain electrons in a fashion to attain what we call a noble gas-like electron configuration. So based upon an atom's position in the periodic table, we're going to make some predictions about the charge we expect, and we're going to focus on our main group elements. Now, the first few we're going to look at, we're going to go over some generalizations and then go over a few specific examples. So Group 1A and Group 2A are our alkali and alkaline earth metals. So Group 1A, it's a metal. They form positively one-charged cations. And these include elements such as lithium, sodium, potassium, rubidium, cesium, and francium. And we're going to go over a specific example. We're going to look at sodium in a few minutes. Group 2A are our alkaline earth metals, and they typically form positively two-charged cations. In other words, they lose two electrons quite easily. These include beryllium, magnesium, calcium, strontium, barium, and they do follow a certain trend in how they behave. One other substance that's actually further on the right side that acts like a metal is aluminum. Let's move this over. And again, we're focusing on main group elements. We'll get to this transition elements a little bit later in our next lecture. Aluminum sits in Group 3A, and aluminum also tends to lose electrons. Aluminum forms positive 3 cations also. So remember, based upon the position in the periodic table, Group 1A, 2A, 3A, they form cations that have a charge equal to their group number, positive charge. Now, over on the further right-hand side of the periodic table, we have our nonmetals. Our nonmetals typically like to pick up electrons. Now, Group 4, we're not going to spend any time on. They're not very predictable. They form multiple charges, so we're not going to really spend any time on those ones. But Group 5A, what we're going to focus on is nitrogen and phosphorus, N and P. Those are two nonmetals that form negatively 3-charged anions. Group 6A form negatively 2-charged anions. Group 7A, negatively 1-charged anions. Group 8A are our noble gases. They don't form ions because they're happy. They have a completely full highest principal energy level, and they don't tend to either gain or lose electrons. So that's just a brief description of the periodic table and how we can make some predictions based upon a position of an element in the periodic table. Now, I'm not going to stop there. I'm actually going to go through a few examples to help us better understand it. So let's move back here, and we're going to begin here in Group 1A, and we're going to look at sodium so we can understand a little bit more. Why do Group 1A elements like to form positively one-charged cations? So we're going to look at sodium as our first example. So sodium. And this is pretty typical for our other Group 1A alkali metals. If we look at sodium in the periodic table, we would see that sodium has an atomic number of 11. It has 11 protons and it has 11 electrons. And if we wrote the ground state electron configuration for sodium, we would see that sodium has a single 3s valence electron. And we said one of the reasons why ions form, whether they be cations or anions, is for the element to obtain what we call a noble gas-like configuration. So let's think about what sodium does. Sodium, being in group 1A, they typically like to lose one electron. So sodium is going to lose this 3s electron, and these usually occur in an electrochemical reaction that we'll learn about a little bit later. And what we form is the sodium cation. Now, the sodium cation is positively charged. We normally don't write the positive 1. Normally, we just write just a positive value. And that's because we know it's 1 positive. And sodium cation has an electron configuration that is identical to the noble gas that's closest to it in the periodic table. So if we look at where sodium's located, let's move our camera over. And let's look at our periodic table. Here's sodium. It has an atomic number of 11. It loses its 1 electron, and sodium is going to have an electron configuration that's identical to neon. Neon has 10 electrons. Neon would have an electron configuration that's the same as our sodium cation. And now sodium having an electron configuration identical to neon, that's one of the reasons why it forms. It's very stable now in that particularly charged state. So that's what we get for our group 1A alkali metals. Let's do one more example. Let's look at beryllium. How about beryllium? Beryllium. Beryllium is in group 2A. Beryllium has an electron configuration, and it has 4 electrons, 1s2, 2s2. So what beryllium does, it likes to lose its 2 valence electrons. And we end up with the beryllium-2 cation, and it has an electron configuration that would be identical to helium, which sits before it in the periodic table. So this explains a little bit about ion formation and how we can predict our cations based upon being in either group 1A or 2A. The charge will be positive with the group number. And in group 3A, the only one I want you to know is aluminum. Aluminum has a positive 3 cation formation. Anions. Nonmetals like to pick up electrons. We're going to look at one in particular. We're going to look at chlorine. Chlorine is a group 7A. It's called a halogen. Chlorine has 17 electrons. If we wrote the complete ground state electron configuration for chlorine, we would see that chlorine is 1 electron shy to having this filled highest principal energy level that would have an electron configuration that's identical to argon. So what happens is the chlorine atom has a tendency to pick up a single electron. When the chlorine atom picks up a single electron, we end up with the chloride anion. It's negatively 1 charged. And the chloride anion has an electron configuration that would be identical to argon. And that's a very important feature as to why ions form. Once again, the tendency to form an electron configuration that is noble gas-like is a very important feature to understand why ions form. So let's go through a couple of examples. And what we should remember, group 6A forms negatively 2 charged ions, group 7A negatively 1 charged, and group 5A, I only want you to know nitrogen and phosphorus, they form negatively 3 charged anions. How about group 8A? Group 8A are our noble gases. Noble gases are not very reactive. Noble gases have a complete highest principal energy level that's filled. And that's one of the reasons why we put helium in the same column as our noble gases. Helium has a 1s orbital, and that 1s orbital has 2 electrons. It's filled, it's happy, not very reactive. So that's an important feature of the noble gases. They're not very reactive. They have a completely filled highest principal energy level. And in reality, what we find is that other elements are gaining or losing electrons to attain that noble gas-like electron configuration. So let's go over a little exercise. What we're going to do is we're going to look at several ions. And what we should be able to do is predict the number of protons, the number of electrons, and the electron configuration for these different ions that are formed. So what we're going to do is we're going to write down the number of electrons and the number of protons for the following ions. And let's also write down their electron configuration. Calcium 2 positive. Now, calcium 2 positive is formed from the calcium atom. So let's look at the calcium atom. If we looked at the calcium atom has an atomic number of 20. The calcium atom, let's write down the number of protons as number P, has 20 protons. And since the calcium atom is neutral, we also have 20 electrons. If we would write the complete ground state electron configuration, this would be the complete ground state electron configuration for calcium. We can always double check 2, 4, 10. I'm counting the superscripts. That's 10, 12, 16. I missed something. 2, 4, 10, 12, 18, 20. We got 20 electrons. Okay, that's the calcium atom. Let's look at the calcium positive 2 charge anion. How many protons? The positive 2 charge cation, it's the same atom. It has 20 protons, but now it's in its ionized form because it's lost 2 electrons. We have 2 additional units of positive charge, and that's why the calcium cation has a positive 2 on it. The calcium cation loses these 2 electrons, and the calcium cation would now have an electron configuration that's the same as argon, 18 electrons. Let's do the same for O2. That O2 is the oxide ion. Let's begin with oxygen. Oxygen is the atom from which the oxide 2 negative charge anion is formed from. Now, if we look at the periodic table, we would see that oxygen has an atomic number of 8. 8 protons. And since it's a neutrally charged atom, it has 8 electrons. And if we write the complete ground state electron configuration, we end up with this electron configuration for our oxygen atom. The oxide anion, which is formed from the oxygen atom, would have the same number of protons. Remember, it's the same atom. The only thing that's changing is the number of electrons associated with that atom. Since it's negatively 2 charged, it gains 2 units of negative charge, and we would have 10 electrons. The oxide anion, and again, we'll learn more about the terminology, would have an electron configuration that's identical to neon. I'll say it's neon-like. Notice that's the driving force to why this ion forms. Let's try one more. The aluminum 3 positive cation. Now, the aluminum 3 positive cation is formed from the neutral aluminum atom. Aluminum, if you look at the periodic table, has 13 protons, and it would have 13 electrons because it's neutral. If we write the ground state electron configuration, that would be the ground state electron configuration for the aluminum atom. Now, the aluminum cation, the 3 positive charge cation, it's formed from this atom, so it still has 13 protons, but now it has 3 additional units of positive charge. So the aluminum cation only has 10 electrons, and it would do so by losing all 3 of these electrons in the highest principal energy level. And you would notice that the aluminum cation also has a neon-like electron configuration. Well, we're going to talk more about atoms and ions that have identical electron configurations when we get into periodic trends. We're going to use a term later, and I'll explain it more. We would say that aluminum cation and the oxide anion, remember, they had the same number of electrons. They were both neon-like. We call those an isoelectronic pair. And we'll get into more of what isoelectronic pairs or groups are when we get into periodic trends. So that's it with chapter 3.5. Again, periodic trends will be our next topic. Thank you.